So much for the introduction. I would like to thank, as many of us do, the organizers for putting together this fantastic workshop. I'm learning a lot, and for allowing me to be part of it and talk to you about how we're controlling and assembling synthetic quantum materials with superconducting circuits. As a disclaimer, I only started my group at NYU a year ago, so most of the results I present today will be from the work I did as a postdoc with David Schuster and John Simon, who are currently at Stanford. Okay, so what do I mean by a synthetic quantum material? Well, I mean these strongly correlated quantum systems where you're combining elements, components from quantum optics and cavity QED to study many-body physics by probing collective phenomena of either interacting atoms or interacting photons. And luckily, I don't need to motivate this research direction too much in this workshop. This is the main focus topic of this workshop, where we've seen a lot of cool talks showcasing beautiful experiments in different AMO platforms. And in this talk, I want to discuss how we can use superconducting circuits to engineer these Hubbard models for interacting microwave photons, where you have this artificial lattice where the photons are tunneling and experiencing these strong on-site interactions. But specifically, I want to focus on what are some of the unique and interesting capabilities that we can use with the circuit toolbox in order to prepare and control some interesting entangled states in this system. So to start things off, to introduce the platform and how we're assembling these artificial materials, let's start with the basic building blocks. Since we're dealing with bosons, it makes perfect sense. It's natural to start to make this out of microwave oscillators. The simplest harmonic oscillator that you can make in the lab is an LC oscillator. So you have this harmonic oscillator, energies are equally spaced. And you can make lattices out of this, but it's not going to be an interesting problem until you start to introduce strong photon-photon interactions, which in our case, we can easily achieve this by replacing our inductor with a Josephson tunnel junction. And this is the circuit for a famous superconducting qubit that we call the transmon qubit. And you can think of the junction nonlinearity. It's introducing this anharmonic energy spacing, an anharmonic energy spectrum. You can think of it about the different ways. You can think of it as now a particle that is confined in a cosine potential instead of a parabolic potential. Or you can think of this Josephson junction as being a very nonlinear inductance that changes its inductance every time you introduce an additional photon, which therefore changes the resonance frequency for the next incoming photon. And obviously, this nonlinearity is very important for quantum computing because then we can perform operations on the lowest two energy levels and treat it as a two-level system. And these are typical parameters that we operate this circuit. But for us, we use this nonlinearity to introduce significant photon-photon interactions. And this is easily seen in this generic experiment that we do in our lab, where we can spectroscopically probe this qubit when it's initially in its ground state, and we find one resonance peak that corresponds to a transition from the ground state to the first excited state. And now to probe this qubit again, do the same spectroscopic measurement, but now we start with a photon occupied in the qubit, and we perform the same spectroscopic measurement. Then we see a very different resonance, and these are two different resonances are split apart by the anharmonicity, and this is showing you how interactions are coming into play. The anharmonicity is now this energy penalty that you have to pay in order to put in an additional photon in this one lattice site. So this is how we're introducing interactions into one lattice site, but we want to look at a lattice. We want to couple these things, and we can easily couple qubits. In our case, we do it by using a capacitor. And when we think about the electromagnetic energy stored in this capacitor, it basically gives us a hopping term that will allow photons to tunnel between two different lattice sites. And we can calibrate this in an experiment where we can put in a photon in one lattice site, bring an empty one into resonance, and then we see some temporal oscillations that it's a good way for us to calibrate our tunneling rates. So then putting together these two ingredients, then we can realize our one-dimensional Bose-Hubbard model, where here I'm showing you an optical image of a tight binding chain of transmons. The transmons are these blue crosses in this image. And where we have our quantum particles, in this case our microwave photons, are tunneling between all of these different transmon sites, and they're experiencing strong on-site interactions because of the anharmonicity. So once we pattern the circuit and put it in our dilution refrigerator, our tunneling and our on-site interaction U, these are fixed parameters of the circuit. The only in situ control that we have of our system is the on-site frequency, or you can think of it as an additional disorder term that we can control in real time. And I'll discuss how we do this in the next slide, but this is the main ingredient that we're going to use for different levels of protocols and for assembling and also controlling these artificial materials. So let me zoom out and show you the whole device. I already talked about the time-binding chain of transmons. You can think of this as where the science happens. I skipped one technical detail where instead of using one Josephson junction, we're going to use a superconducting loop of two Josephson junctions. This is a superconducting quantum interference device, a squid loop, where having these current bias lines that are inductively coupled to the squid loop allows us to tune, to thread magnetic flux in this loop and essentially tune the Josephson energy or the inductance of this effective Josephson junction. This allows us to essentially tune the resonance frequency of all of our qubits. From a material perspective, you can just think of this as now we're having both real space and time control of the lattice potential. And additionally, we can also have site resolve microscopy where we're coupling each individual qubit or transmons to read out to microwave oscillators at different frequencies, and we're operating in a dispersive cavity QED regime where we can probe the occupation of this transmon, whether if it's in the ground state or in the excited state, by looking at the dispersive shift of each individual readout cavity, or by, in this experiment, we're doing single shot histograms where we can see that the IQ response of the cavity is very different depending on the occupation of our transmons, and we can get single shot fidelities of around 80 or 90%. So what are the parameters of our Hamiltonian? Compared to the lifetimes of our microwave photons that are living in each individual qubit site, we have that our tunneling is about 3 or 4 orders of magnitude faster than the decay. So we're in this quantum coherent regime, and our on-site interactions, our anharmonices, an additional order of magnitude larger than the tunneling. So we're in this many-body regime where we're actually dealing with hardcore bosons confined in this one-dimensional lattice. So there are, of course, many groups around the world trying to make these Bose-Hubbard models with superconducting circuits, and it's an exciting field. We don't focus so much, so the science that I'm going to discuss only has like 7 or 8 sites, so we don't focus so much on trying to build a platform that has the most number of qubits, but we're trying to intellectually contribute to the field by coming up with, we're trying to contribute by simply trying to answer these questions. How can we guide many-body systems to some target highly entangled state? And this is not just relevant for many-body physics, but obviously this can have applications for both quantum information and metrology. Also, how can we efficiently probe these correlated states more efficient than doing tomography on all the qubits? Yes?
Can you change the sign of U?
Not in this device. With other qubits, you can change the sign of U to go from this is attractive to repulsive. We can talk more about like instead of a transmon, you could probably use a fluxonium qubit or a flux type qubit. It's a little bit more complicated, but that's what you need to do. And one other important question we try to ask is like, does the superconducting circuit platform offer any useful or interesting capabilities in comparison to other AMO platforms? And I always like to show this honest cartoon because, in most AMO platforms, you have this clean system where all the atoms are the same. And as much as we try to fabricate all of our, nanometer scale Josephson junction to have the same size, we really just have a macroscopic circuit where all our atoms are not the same, all our junctions are not the same. So we have to deal with this disordered solid state system. And additionally, since we're dealing with photons as an open system, so we have to deal with dissipation. And it turns out that you can actually use these imperfections to sort of make materials from photons. You can use dissipation to stabilize some incompressible states if you have a many-body gap. And you can also, but what I'm going to focus on in this talk is how we're going to use disorder, or more specifically, a precise site resolve control that's coming from this overhead that we need to have to be able to tune our qubits to an ordered state. We can use it to make certain types of states, entangled states, and also ways to probe dynamics. So this is the research team that in both my postdoc lab, but as well as in my own lab, we're trying to come up with new preparation schemes and new techniques for probing and controlling these artificial materials. I'm not going to go through all of these results. I'm just going to highlight again this idea that we can use site resolve control to prepare some correlated photon fluids, study some transport dynamics in these fluids, and look at some interesting entangled states and how we can probe them with Ramsey interferometry. Okay, so the first demonstration using precise site resolve control to prepare these fluids, I'm highlighting in this diagram here, where we're going to intentionally introduce a lot of disorder into the system by detuning our qubits such that we are, if we're sort of quenching away any tunneling dynamics, such that if you talk about what is a many-body state, in this case, it's just a boring product state, and we can easily prepare this, and in principle, any type of state in this material through particle-by-particle assembly, which is just a fancy way of saying I'm just going to pi-pulse the qubits that I need in my lattice, and now if I want to prepare a fluid, then I'm going to control the disorder and remove it slowly such that we're satisfying the adiabatic theorem, and we're going through this trajectory, we're staying in the same instantaneous eigenstate, and we're delocalizing our photons through tunneling-induced quantum fluctuations into this strongly correlated fluid. And then at the end of this protocol, we using our microscopy for our readout resonators, we can measure on-site occupation, we can measure correlations as well as coherence. So this is our protocol, and as always, it always makes sense to benchmark it with the easiest thing you can do. So we're doing this warm-up by trying to melt single photon, single particle in the box eigenstates. These are things you see when you take undergrad quantum mechanics class. So here I'm showing you the dependence of the eigenstates and the eigenenergies as a function of disorder. Here it's time, but we're changing disorder as a function of time. When we're strongly disordered, again, what we have is just different. We have a photon localized in one of the 7 sites. And in near zero disorder, we're just going to have different quasi-momentum states. And adiabaticity just ensures that we have a one-to-one correspondence to where we initially put our photon and which case state or quasi-momentum state we delocalize into. And here I'm showing you data where we're performing this protocol and we stop the preparation at different places along this trajectory. I'm showing you the density profile, like the number of the photon occupation in each individual site. So this is a 7-site realization, and you can see they usually start localized, and then as you get closer to near zero disorder, then you get your sin kx eigenstate, and you can do it as well for the other eigenstates, but for the purpose of time, I'm just going to move on and ask the question, how can you actually tell that you're adiabatic? And the question is, oh, well, if you want to prepare a single particle, then you just look to make sure you get the right density profile. But then that question becomes very complicated when you want to melt multiple particles, and then you have to benchmark the adiabaticity by performing tomography on a complicated entangled state. So instead, what we do is we try to do this reversible state preparation protocol where, again, we prepare localized photons by pi-pulsing individual sites. And here I'm showing you what the protocol looks like for a single particle, but we do the same thing for multiple particles. Then we remove the disorder by ramping down the qubits such that they're on resonance. And then we reversibly reinstate the disorder with the same ramp time to go back to the localized regime and ask the question, did I relocalize the initial states? Because that's how we benchmark adiabaticity. Did I come back to my initial state? Did I relocalize the photon into the initial transmon state that we originally excited? And then we can vary this ramp time as we do an experiment over 4 orders of magnitude. And we see that if we ramp the system to order too fast, much faster than the tunneling time, then yes, I recovered the photons, but no dynamics happened. The photon didn't even have time to go to its neighbor. Now, if I go slower than 1 over the tunneling, then yes, I do start to recover my photon in the original site. So this is where we start to get adiabatic dynamics. And you can see that if you really want to be adiabatic, you could ramp this as slow as you can, but then you're fighting with T1 loss, you're fighting with photon loss. So this is why you see that this population is not exactly one, it will start to decay as we go to longer ramp times. And then if we're in this intermediate regime where the ramp time is of order 1 over the tunneling, then you start to get that your photon that's delocalizing is going through these diabatic transitions, and now you're starting to excite other qubits, and the qubit that you are originally looking at, that's why we're seeing that it loses occupation. So this is how we tune adiabaticity, and we want to operate there. And we do the same for multiple particles, and this is how we calibrate our ramping procedure to do this. So now we can delocalize free particle to prepare a free particle fluid. Here I'm showing you the many-body eigenspectrum for the band of states that have a total number of particles equals to free. We prepare, in the disorder case, the highest energy state by putting photons in these free sites, because those are the qubits that are at the higher frequency in the disordered limit. And then we follow this trajectory by removing disorder, and we can see that these free photons will delocalize into our entangled fluid. And we can do this for 2 particles, 3 particles, and 4 particles. And here again, I'm showing you in this color plot what the density profile looks like in strong disorder, and then you ramp it down to near 0 disorder. And here at the bottom, I'm showing you the density profile for our fluids for different number of densities. And you can see, and you can see this clear observation that the profile of the fluids actually has a strong dependence on the density. And this is offering some insight that interactions are playing a role in terms of how the photons are organizing themselves. And this becomes obvious if you start to do some theory. I don't do much theory in my life, but luckily this was something that worked out. Because if you take the 0 interaction limit, then you expect that all the fluid density profiles would have the same shape, would have the same single particle shape, your sine kx density profile. But now if you take your analytical many-body ansatz wave function, and now you put this penalty through these contact interaction terms to have a penalty to have two particles on the same site, and then you calculate what is the expectation value for your density profile, then you start to see that your theory is now agreeing with what you're measuring, that the density profile now scales with the number of, it has a strong dependence with the number of photons you're delocalizing, and it's sort of implying that the collisions are shaping the density profile. But in terms of ordering, how can you probe what is the ordering of the photons as they delocalize and interact? Then you have to measure some correlation functions, some correlations between the photons. And this is where we measured the G2 pair correlation function, is the probability of detecting 2 photons separated in the lattice by distance x. And here I'm showing you the data for the G2 as a function of different fillings, or different number of photons in our 7 sites. So these are represented by different colors, which I apologize if it's not super clear in this projector. But what we see is that, yes, you have an anti-bunching spatial region, and this region scales with the density, and this follows from basic intuition that as you put in more photons, they have less space to delocalize before they interact with each other. And now if I take this x, and this dotted line corresponds to a parameter-free Tonks-Girardot gas theory, as that's what this model corresponds to. It corresponds to hardcore bosons confined in 1D, so that's why we were expecting to see G2s that match the Tonks gas theory. And if we take our spatial coordinate and rescale it by our density, as shown in this inset, then we start to see that these correlars are actually collapsing onto this, onto the G2 for the Tonks gas. We're starting to see these tiny Friedel oscillations, these small oscillations in the correlations, that is a direct evidence of the fact that our 1D, our hardcore bosons confined in 1T are behaving as non-interacting fermions. Okay, so this was the part of the story where I showed you how we can use precise site resolve control to prepare these interesting correlated fluids. Then you can ask, well, can we, and this was essentially preparing some low entropy and excited state of your system, eigenstate of your system. But you can also ask the question, can you look at dynamics as well? And the answer is yes, we can leverage site resolved control for probing some out of equilibrium dynamics. It ends up being some quench protocol where now instead of melting our particles onto a lattice profile where all the qubits are in resonance, let's try to melt them into a profile, through a density perturbation that matches some cosine of kx shape. So let's say if we want to excite the system to some long wavelength excitation of the system, it turns out that after we immediately quench the system, after adiabatically preparing the state, and then we quench the system to bring all the qubits on resonance, the state that we adiabatically prepare now corresponds to the superposition of the low-lying eigenstates in our hardcore band. And since the dispersion for hardcore bosons in 1D is linear, actually these excitations that we're preparing are actually phonon modes, phonon excitations of our fluid. So once we prepare the superposition, then we can start to measure the density perturbation as it's propagating in the lattice. And that's how we can measure essentially the speed of sound of our photon fluids. So here I'm showing you this experiment for 1 photon, 2 photon, and 3 photons by melting our fluid at the density perturbation and then letting those phonons propagate in the lattice. And this solid line corresponds to the center of mass. Effective center of mass, and this allows us to sort of probe what is the velocity, what's the sound velocity, and we can see that the sound velocity scales or has some dependence with the density or with the number of particles you have in your system, and that's expected again from Tonks gas theory that your sound velocity matches your Fermi velocity, and it has a well-defined dependence with the filling of particles in your lattice. And again, the takeaway message is that this is showing you that just, again, the strong interactions are impacting also the collective motion of your particles, not just how they order when you adiabatically prepare your fluid, but also their collective motion. So how much time do I have? 10 minutes? Great. So I'm going to change gears a little bit, and I'm going to ask this probably weird question. Is can we actually leverage quantum computers and interface quantum computers with these synthetic materials in order to come up with new techniques to be able to probe them and assemble some interesting entangled states? And where I'm coming from this is that so far what I've showed you, all of these experiments that we did with our fluids, our preparation protocols have so far relied on the classical control of the lattice. And let me unpack that. What do I mean by that? What I mean by that is that, yes, you do these quench experiments or you do these adiabatic trajectories, but in the end, what you do is you apply some currents through some bias lines to apply some magnetic fields to tune the frequencies of your qubits. But then again, you're using qubits as lattice sites, so can you actually leverage the quantum nature of your lattice sites? And can we essentially think about having a way to have quantum control over your lattice configuration? Yes, in the end, of course, you still have quantum objects, you still have quantum particles, but can you actually have quantum control over the lattice configuration in a way that it would allow us to steer the dynamics and maybe the entanglement in a different way that we would normally be able to do if we just had classical control over our lattice? So this might sound vague, so let me try to focus more the story here. So we were then thinking about transport in the system and how if we can have a lattice configuration that can depend, for example, on the quantum state of one or several qubits, that will be our control qubits, then now we can think of a way in which we can control the many-body dynamics through a lattice configuration that can be a superposition of different configurations. And now we can think about now interfering the unitary dynamics of different types of realizations. The easiest thing that we could do in this vein, in this story, was to think about making a photonic transistor, shown here in this cartoon. So what we're trying to do is, let's imagine that we're going to have three particles that are going to be localized on the left-hand side, and they're in this sort of quasi-disordered regime where the particles on the, well, it's your left, are in the highest they're at a higher energy or a higher frequency, and then I'm going to adiabatically bring them below the right-hand side. So if adiabaticity is satisfied, then you would expect that these now particles, or whatever quantum state you have there, would get shuttled on the right-hand side. But what we want to do with this transistor is we want to have a middle qubit that will control this transport, that its quantum state will control this transport. That if it's empty or has 0 photons, the particles or the state will remain localized on the left-hand side, but if now this ancilla qubit is now excited with 1 photon, then that will allow the transport of particles to go through the other side. So that's why this analogy with the transistor. And so that was the idea. Can we demonstrate this? Because this would be the easiest thing to demonstrate this idea of having quantum control of your lattice potential. So this is the protocol. Again, we're going to start we're going to pi pulse our qubits in the disordered regime. We're going to put them on the left-hand side. And then what we do is we're not going to adiabatically move them to all the qubits being on resonance, but we're going to move them to this transistor configuration where the middle lattice site is detuned by its interaction energy, U, by the anharmonicity. So what happens when you do that? When you do that, basically now you're in a situation where the resonant tunneling going through this ancilla qubit is now not going through the first excited state, but it's going through the second excited state. So resonant tunneling will only be allowed for the F state, and this can only be allowed, you can only have 2 photon in the sites if you have a photon to begin with. So now you have that the transport will be conditioned on the occupation of this site just because of the fact that, you know, this is a bosonic site, and you're putting on resonance your E states on the left and right side with your F state in this ancilla qubit. So in this case, because our middle qubit is empty, even though I'm going to do this thing where I'm going to melt the photons into this configuration and then reintroduce disorder, but now I have this inverted configuration where now the right-hand side qubits will be at the higher energy, nothing's going to happen. I'll still have that my particles will be localized on the left-hand side. But now, obviously, this changes if I now have a photon in the middle control qubit, and then I'll have that the 2 photon state of that control qubit will mediate the delocalization of our particles into the similar type of fluid that I talked about before. And then when you introduce disorder, then you have that now the photons are now coming back, but they're relocalizing on the right-hand side. So you can in principle think about this as a conditional few body swap operation. But really to highlight this protocol, right, which was the whole motivation about thinking about this idea, is now that you can prepare your auxiliary, your control qubit now in a superposition of having a particle and a hole or 0+1, which you can easily do with a pi/2 pulse. And then you let the system adiabatically evolve in this transistor configuration, and now you're preparing your photons into this coherent superposition of being both in a solid and in a fluid state. And this maps now to, when you reintroduce the disorder, now this maps to this funny looking cat state or noon state, where you have a superposition of having photons on the left-hand side and photons on the right-hand side. And obviously, as you already know, if you really want to probe this site, but just by doing local measurements, then you're not going to get absolutely no information. Just locally, you're only going to see a mixed state. The population of each site will be half. So what you need to do is actually ask more of your ancilla, not just to be able to leverage quantum control of your transport, but also to do Ramsey interferometry on this ancilla to probe the long-range coherence of your entangled state. Why do we do Ramsey interferometry in general? Well, the oscillations already tells us that we have a coherent superposition. I'm just telling you what happens in a single qubit case. And the frequency, for us experimentalists, that's a great way for us to calibrate what is the qubit frequency. That's the most precise way we can calibrate our qubit frequency. So I'm showing here the data for our ancilla qubit when it is uncoupled from our lattice. And this is its fringe frequencies with some reference frequency. But now if we adapt this Ramsey protocol to our controlled transport in the many-body regime, then so we excite our qubits, and then we apply our ancillas in the pi/2 pulse, and then we apply this transport protocol where we prepare our noon state, and then so we entangle the system, we let the system evolve for some amount of time such that we're accruing a relative phase between the 2 components of our cat. And then we're reversing the transport procedure in order to disentangle the qubits and relocalize the phase information that we want to measure into our ancilla qubits, such that when we apply a pi/2 pulse and measure along the z-axis, we're going to measure some Ramsey fringes on our ancilla qubit, and we see that those fringes are much faster. They're much faster because now you're accruing this additional phase that corresponds to the energy difference between the left-hand side and the right-hand side of your cat. And we can see that by looking at the Fourier transform of our fringes when the control qubit was unentangled and it was entangled with our qubits. And we can see that the energy difference between these two Fourier peaks exactly corresponds to the energy difference between having the free photons localized on the left-hand side and the free photons localized on the right-hand side. Since I'm running out of time, you can ask me how later, maybe during, after the talks, how we normally would go from our Ramsey signals usually look like this, because I lied, like our Ramsey signals don't really look as good as this if we just perform a simple Ramsey measurement. Turns out that in order to get better contrast in our fringes, we have to, we're limited by dephasing time, but since our T1s are much longer, we developed an echo protocol where we can echo away the noise in these ramps, adiabatic ramps, because that's where we spend most of our time evolving our many-body system. We don't spend so much time idling in the noon state. And by just applying a single echo pulse, we can cancel out the dephasing noise, and we can, increase our Ramsey fringe contrast. Again, it's just a technical detail, but I'm happy to talk about it a bit more because it's sort of a many-body version of an echo if you think about what happens in the effective Bloch sphere because of dephasing from all the different qubits. And let me just end by saying that another way that we benchmarked the entanglement structure in our noon states is actually think about it as a sensor. Now, it's obviously not a useful sensor. It was just a way to benchmark our system. Because in principle, if we measure our Ramsey fringe to be at some particular frequency that just so happened to match the energy difference that we were hoping to get, maybe we were lucky. So what we did instead was, let's see how sensitive these noon states are to some perturbations that we introduce. What happens if we tune, during this Ramsey whole time, we tune our qubits from the left down by delta and the qubits on the right up by delta, how much this fringe frequency change, right? This is basically the whole idea of metrology, this phase sensitivity, how it can be enhanced and through entanglement. And we indeed see that both for a 5-qubit noon state and a 7-qubit noon state, we see that the Ramsey frequency is being shifted as a function of delta, but you get an enhancement that scales with the system size, and this is your Heisenberg limit, and this is showing us, this was just a different way of clearly seeing that we indeed prepared this noon state just by looking at it as a sensor. So with that, let me wrap up and summarize. I've showed you a few techniques in which we use some. Normally, you would consider them imperfections. In our circuit toolbox, we use them as resources to prepare and probe and control different types of many-body states. And maybe some of these things will be useful as we scale up these systems to more and more qubits, because this was only done with 7 or 8 qubits. With that, let me just acknowledge the Schuster and Simon groups, especially the students who were in the quantum simulation team, our TLE collaborator, Caden. And let me just say that I'm starting a group. It's fun, and at NYU, we're doing quantum science on Broadway, so you can also do that on Broadway nowadays. And just to leave this, in case it stimulates any interesting conversations, I'm now building these Bose-Hubbard models, but I want to not only think about new schemes of preparing states and controlling them, but also like upgrading the Hamiltonian. So I want to go from not just having strong on-site interactions, but having a way to program arbitrary two-body collisions between the photons. Thank you so much.
So thank you for the talk. Now there is time for questions.
I had 2 questions. Can you tune U in your experiment?
No, it can't be tuned. I think we can tune it. It's a similar question to how we normally can tune the sign. And those types of qubits, we can also tune the magnitude of U.
And the other question was, can you also introduce controllable dissipation, like just oscillate qubit loss in your system?
Yeah, so this is Let me see if I have a backup slide. This is work done by the postdoc before me, but I think maybe this might be useful to talk. Okay, I do have that back. So we do engineer these reservoirs that are a combination of having a lossy resonator coupled to another transmon qubit to have energy-dependent loss. So this would act as a stabilizer to stabilize a photon and shuttle it into our qubit lattice and prepare a Mott insulator. And it works well for any type of incompressible state you have a many body gap. So first of all, yes, you can just couple lossy oscillators at different sites. If also it becomes a spatial question as well. You just have to use drive-in dissipation, and you can come up with interesting ways to stabilize some entangled states.
And you can get like more high dimension, like 2D lattices as well.
Yes, you can do more two-dimensional. Then it becomes a technical challenge that each one of these qubits needs like free control lines or free things need to couple to it. So once you go to 2D, then things need to cross. It's obviously doable. Obviously, IBM and Google have to do this with flip chip technology, but also there are academic groups doing this as well.
Thank you.
Thanks for the talk. About the Heisenberg limited scaling, you mentioned it's not useful as a sensor, but I wonder if you've thought, okay, people do use squids, and what would it take to do something useful for a squid person to kind of get something out of this?
Well, a squid person normally would put the squid close to a solid state surface. And now you're saying, can we put these multi-qubit Noon states on top of a solid state? I mean, it's also a good way to probe the solid state environment on the substrate into which we pattern our transmons. But we actually also see this because the Noon states are equivalent to GAZ states from a local control perspective, and we can see that because we have this correlated dephasing, our GAZ states are much less lived than, like they dephase much faster than our Noon states. I am thinking about ways in which we can use these types of multi-qubit entangled states for doing sensing, but not so much for like solid state things happening on a substrate, but more on detecting photons, where you can condition your way in which you can receive a photon to stabilize itself into a Noon state instead of just asking local questions on each individual qubit. That's normally a quasi-particle limited problem. You're just asking questions about, did I prepare the entangled state or not? And that just becomes a Ramsey interferometry measurement. But yeah, maybe there are interesting things. I mostly said it's not interesting because I'm intentionally introducing these perturbations. But normally you want it the other way around. You want to see, and maybe this is something that could be done, but I think maybe the issue there is that our T2s are not long enough to be able to really map out the really slow varying fluctuations in our qubit frequencies, if that's something that people are interested in.
Yeah, first maybe comment on the questions on the tunable U. So the U is not tunable, like you said, but there's ways of making a tunable J, like tunable couplers, and then it effectively gives the same thing, but not changing the sign of U. Yeah, magnitude. But then question, so regarding the adiabatic preparation method, so how do you see the scaling of that when the number of qubits increases? You can expect smaller gaps. Yeah, any comments on that?
So with the dissipation engineering, so we're thinking about using dissipation, or at least my postdoc group, and we were kind of working on that before I left and the lab was moving. But we were trying to do sideband type of cooling techniques with dissipation to be able to essentially deal with this problem where if it's a compressible state and you don't perfectly prepare your ground state, but you prepare some phonon excitations, you can think of ways in which you can do sideband cooling to cool some of those phonons to get closer down to your eigenstate. But then there's also, I know Giovanna has worked on this, and I know that the Lucan group has also developed some interesting protocols for doing shortcuts to adiabaticity. So did I get the, because I remember I saw a talk you gave on shortcuts of adiabaticity. And they had a much larger system, and I think that is also a good approach to tackle. But you're right, as you scale to longer systems, this is why people like to work with gapped states when they have to do error correctional or any type of things.
All right, good, thank you.
So I have a question regarding the adiabaticity you were showing. So there seems to be, when you go from this adiabatic through the diabatic regime, there is a bump that doesn't go down the curve, but you see that there is a more irregular shape. Do you understand where it comes from?
In the diabatic,
Right. Here, exactly, the other figure, this one. Yes.
Yeah, so two things here. Dotted lines are theory, and then the dots are the data. The discrepancy comes from the fact that when we do the theory, we're assuming that we're sending in a specific shape of our ramp, but in our experiment, because we have different dispersions for our waveguides, it's not actually the ramp that the qubits are seeing. But at the end of the day, we still calibrate the ramps that the qubits are experiencing. But this is why we have a discrepancy with the theory. And are you referring to maybe this bump or?
Exactly. No. Yeah.
I have not thought about it because I mostly was focusing on getting to the star. But if I had to guess, when you go a little bit faster, maybe you do have some diabatic transition, but you don't leak out into other branches as much. Or maybe you do have, sorry, what I mean to say is like maybe you have some refocusing in the middle where you somehow these things cancel out in a way in which you now have, for that specific ramp time, a higher amplitude going through that branch. But also it's very dependent on the type of ramp you choose. Right here, so we're using an exponential ramp, so we're going fast at the beginning when the energy differences are large, and then slow when they get very small. And by T ramp, we're just varying sort of that same shape. So it's sort of hard to say where that's coming from because it's also very ramp dependent. If we did linear, maybe maybe funnier things would happen in this diabatic.
So you have room for optimizing and perhaps make the transfer more adiabatic.
Yeah, this was just to optimize it to just see the occupation come back. We didn't care so much about what was happening here. The moment we start to see things go down and come back up, we knew that this region is not a good region to operate.
Okay. So perhaps I have another question. And how, do you read in the Ramsey signal the size of the null state?
I would say that now I also realize that this cartoon is wrong because here there should be some pi pulses, but essentially we choose our size based on the number of qubits that we pi pulse, and we can detune some qubits away. But it's hard to tell from the Ramsey, if you don't even know the size of your cat, how many qubits are entangled. If you assume that you have this many qubits, then you could use the Ramsey frequency as a way to verify that the energy difference matches the energy difference between the two, between having 2 or 3 photons on here and 2 or 3 photons there. If it was a different frequency, then it will kind of be hard to tell. Maybe one easy way to tell it is you now introduce perturbations during the Ramsey. This is how we did that, the sensing thing. So now if we see that one qubit is shifted up or down, but your Ramsey frequency does not care, then maybe that's one way to benchmark that, okay, we're not entangled with this qubit, like there are no photons living there, or photons living there are not entangled with our ancilla.
So, if there are no further questions, we thank the speaker again.
Thank you.